Exam review question related to product distribution of radicals. Assume that the free radical chlorination of alkanes proceeds at the following relative rates. Draw all possible monochlorination products using isohexane as the starting material, including all stereoisomers. Calculate the percent yield for each isomer. So in calculating product distribution, we need to know the propagation steps of free radical substitution. In propagation 1, we form the alkyl radical. That's by the abstraction of a particular hydrogen. So we lose a hydrogen in propagation 1, and we form the alkyl radical. In step 2, a halogen radical can react with the alkyl radical to form the alkyl halide. But the formation of any alkyl halide up until now depends on two factors: the number of hydrogens that are abstracted and the relative rate of abstraction, which is given in the problem. So let's derive the formula. The percent yield of any particular product X is equal to the relative amount of that product divided by the sum of all relative amounts for all products multiplied by 100%. Now we said the relative amount of the formation of a particular alkyl halide depends on two factors: the number of hydrogens that can be abstracted and the relative rate, which is given. If we divide that by sigma Ra and multiply by 100%, we get the percent yield. So from this simple derivation, we know that the relative amount of a particular product depends on the abstraction of hydrogens and the rate of formation. So let's start deriving structures that we can form. First, let's draw isohexane in its full Kekule structure, meaning we show all of the hydrogen. So the structure of isohexane starts with pentane, and we put a methyl group on position 2. So just by drawing this, you can already imagine where the substitution can occur. So the first structure I can think of is to substitute the chlorine on carbon 1. And in this case, we don't form a chiral center, so no racemic products will form in the formation of 1-chloro-2-methylpentane. We can form the tertiary alkyl chloride by replacing this hydrogen with a chlorine. If we move down our carbon chain, we can substitute the chlorine on carbon 3 and carbon 4. But in both cases, we form a chiral center. The formation of the radical at carbon 3 in propagation 1 results in a planar compound at carbon 3, just like a carbocation. With carbocations, for example this carbon being the carbocation, we said that the bond angle is 120 degrees. The molecular geometry here is trigonal planar. We have an empty p atomic orbital, which contributes to the planarity here. That means nucleophiles can attack from the front or back, resulting in a racemic product. In the case of radicals, we have a partially filled p atomic orbital. This also contributes to sp2 planarity and means that in propagation 2, bromide, for example, can attack from the front or from the back, forming a racemic product. So because of that, the formation of a chiral center results in two stereoisomers, two enantiomers. So the chlorine can be projecting out front or towards the back at carbons 3 and 4, if the substitution occurs at those positions. Finally, we can substitute a chlorine at position 5 to form another primary alkyl chloride. And because we don't have a chiral center forming, only one product results. So essentially, if we react isohexane in Cl2, dichloromethane, and light irradiation, we can form 7 different products. The next step is to calculate the percent yields for each one of them. To begin, we need to know the number of hydrogens that were abstracted to form the particular product. We also need to know the relative rates which are given. If we find the product of those two, divide that by the sum of all relative amounts, and multiply by 100, we have the percent yield of that particular product. So essentially what we need to do is look at the number of hydrogens that are abstracted for the formation of each product and multiply it by the given rate. Let's look at compound 1. In compound 1, we form the primary alkyl chloride by abstracting any one of these 6 hydrogens. These 2 carbons are chemically equivalent. You can place the chlorine on this carbon or this. It would be the same. So the number of hydrogens that can be abstracted are 6, and the relative rate is 1. So we multiply the rate, 1.0, multiply by the number of hydrogens, and we get 6. We do the same for products 2 through 7. Solving for sigma Ra, we obtain 48. The final step is to put the relative amount of a particular product over sigma Ra and multiply by 100. That's the ratio that gives us the percent yield for that particular product.